This time we're going to be working on section 2.5, and section 2.5 again deals with zeros of polynomial functions. Bar zero of polynomial functions. Okay, so that didn't quite work as well as I thought it was going to with the labeling, but you guys know what we're talking about here. So zeros of polynomial functions. I might have to just stick to the free handwriting. Alright, couple things to set this one up. We've got fundamental theorem of algebra we're going to talk about, and then we're going to get into a couple different tests that we can work with on working with polynomials to simplify some of the work we're going to do down the road here. So, first thing I'm going to talk about, like I said, is fundamental theorem of algebra. And the main application that we're going to deal with this is just understanding how the complex number system plays into our polynomials here. And what the fundamental theorem of algebra says is if we have a function f of x that's a polynomial that has a degree of n greater than 0, so positive degree, then that function has at least one 0 in it that's from the complex number system. Alright, so how is that really going to help us? Well, when we ran into some of the things from complex numbers in that last section, it kind of opens up the door a little bit to help us find some more factors that didn't sit or didn't play out in the real number system. So another thing that goes with this would be linear factorization theorem, and it just piggybacks a little bit off of the fundamental theorem of algebra. So again, the linear factorization theorem. And this puts a little more clarity into how we're using the fundamental theorem of algebra with this section. So what it is this. It just tells us that if I have some polynomial, I should be able to factor it down, and again, linear, first degree, into something that's going to look like this. However far we want to take this out to x minus c sub n. And of course we can have a constant that we can factor out in front as well if there's a common constant. Now the big thing on this, the C1, the C2, all the way up through the Cn, each of those are complex numbers. Now the other part of this that this lets us say is if we have something that is to the nth degree, let's say we have f of x equals 2x to the 7th plus so on and so on and so on, this, by introducing the complex numbers with this 7, in the past we said we could get up to 7 different roots, or 7 different zeros at the most. Now, because we're throwing in complex numbers as well as real number solutions, we'll have exactly 7 solutions to this problem. So that's where we're going to go with this. Now, one other test that we're going to look at here is called the rational zero test. And our rational zero test is basically, it's going to help us find possible rational zeros. So again, if we're starting with a polynomial that looks or takes on this form, and you've seen this before in some of our other productions in class. A sub n times x to the nth plus a sub n minus 1 times x to the n minus 1, and so on. So just our basic form that we've seen a lot of already. For our standard form for a polynomial. If we've got that, what our rational zero test is going to tell us is this. If there is a rational zero, we're going to be able to find it. And this isn't writing very well, I apologize. Our rational zero is going to take on the form of p over q, just like a rational number when we did an integer over an integer was a rational number. If we're going to find our rational zero, what's going to happen is the value from p is going to come from a factor of my constant, a sub 0 out there. The q value, it's going to come from a factor of a sub n, or our lead coefficient. So let's take a look at one use of this and where we're going to go with this as we lead further down in the problem here. So let's look at an example. Let's start with this polynomial, f of x. F of x equals x to the third plus x minus 1. Alright, so our p-values are going to come from the negative 1 out here. Our q-values are going to come from our lead coefficient of 1 here. So this one's not going to be too tough. The values for p, like we said, they're going to come from factors of negative 1. Well, that could be a positive 1 or a negative 1. Our values for q are going to come from the lead coefficient out here of 1, which would also give me factors of plus or minus 1. So what that tells me is, if I try to write this as my rational zeros, p over q, I'm going to get plus or minus 1, well, let's go through here, plus or minus 1 over plus or minus 1, which just simplifies into plus or minus 1. So basically what we just found there was plus or minus 1 is going to be the only options for my possible rational roots. Or, like we've been working with in this term, zeros. So the only thing that can possibly be my x-intercepts in this that are rational would be 1 or negative 1. So one way of looking at that would be to say, alright, let's find f of 1. So that would be 1 times 1 to the third plus 1 minus 1. So not real exciting here. 1 times 1 is 1, plus 1 minus 1 just ends up being 1. Now again, since that's not equal to 0, that just means that that's not going to be one of my roots for this problem. So our other possible one, f of negative 1, we would just do the same thing. So 1 times negative 1 to the third plus 1 minus 1, and simplify. This is going to become negative 1 times 1, which is negative 1, plus 1 minus 1, which gives me negative 1. So just like in this other one, also not equal to 0, so it's not a root for this problem either. So what that tells me is, if I were to factor this or graph it or whichever way you're going to solve this to find our zeros or our solutions, basically it just means I'm not going to have any rational zeros for my problem.